Hello students. So have a look at the figure, the sketch. Here is a body of infinite heat capacity. So it's a source. The sink is at 200 Kelvin, the source is at 1000 Kelvin. This body is, the heat will flow from this body, and we would like to know how much of that heat can be converted into work, theoretical maximum amount, and that is called as available energy, right? Here is another body which is a fluid. Its temperature is also 1000 Kelvin as this is, but this body cannot be considered as body of infinite heat capacity. Why? Because the moment heat starts flowing out from this body, the temperature of this body will start dropping. Okay, and so what we will consider now, we will consider these two cases, and we will find out what will be the available energy of the heat which flows from this body and from this body. We will separately and slowly consider that and make the sketch of the temperature profile and entropy change, of course, on this TS plane for each of them, and that's very instructive. Okay, so if there is let's say certain amount of heat, I will say Q is flowing out, and then if we want to find out how much of this heat can be converted into work, what is the theoretical maximum potential, right? So if you want to find out that, you need to imagine that this heat is transferred to a Carnot engine which is running between these two temperature limits. That's what has to be assumed. Okay, and then if that Carnot engine, the work that Carnot engine produces, that will be the available energy of this. Okay, so how do we? So essentially, what we are doing is, if this is heat transferred, then we have to imagine that there is some Carnot engine which is run. So this heat is given to Carnot engine. So this is Q. This heat is given to Carnot engine, and there will be some work, and this is nothing but the available energy. This is the maximum work because you are running a Carnot engine. So this is available energy. So if it is, this is the available energy of Q. Remaining will be unavailable energy. Right? Okay. That will be flowing out. This will be unavailable energy. That will be rejected to the sink. So you are operating between source and sink. Now see, just pay closer attention here. Heat is transferred from source to Carnot engine. It has to be transferred reversibly because Carnot engine is a reversible engine. Meaning what? The temperature of the engine, when I say engine, what I mean is temperature of the working substance of the engine. This engine is imaginary, so that working substance is also imaginary. But it's a theoretical engine, imaginary, you know that. So temperature of the working substance should also be 1000 Kelvin. Only then it's possible to have reversible heat transfer. So heat transfer is reversible means temperature of this Carnot engine is also 1000 Kelvin. When heat is transferred, what will happen to the entropy of this Carnot engine or the working substance in the Carnot engine? That will increase, right? That will increase. And how do we show it here? We will say this is also at 1000 Kelvin. This. So we are showing here the entropy change of this the Carnot engine or the working substance of Carnot engine. And since temperature here is constant, temperature here will also be constant. It's at the same level and heat is received. So this entropy is going to increase. So you can say initial entropy some value, and this is, I'll say, this is T. This will be 1000 Kelvin. Let's see. So your initial value here, and the entropy is going to increase, but the temperature is constant. So this is what we show. Okay. So this line represents the increase in entropy at constant temperature in this situation. In this situation. Okay. And then of course you can then the whole cycle will be, you can say this will be 200 Kelvin, right? 200 Kelvin. So the entire cycle will be your regular Carnot cycle. Regular Carnot cycle. Okay. So here you can see the heat transfer Q is this entire, because 1 to 2 is heat transfer, 2 to 3 is reversible adiabatic expansion, 3 to 4 is reversible heat transfer, meaning what? Heat is transferred from the Carnot engine to this reversibly. Again, the temperature of this engine when heat is transferred will be 200. Why? Because it is reversibly transferred. So this is 200 Kelvin. So you see this total area under 1 to 2. Total area. We can show this by blue color. This is the value Q, heat supplied to the engine. Whereas area under 3 to 4 will be heat rejected by the engine, and that we can show by. Okay. So this total is Q. This is heat rejected. Okay. We can consider this as Q2. So this is Q2. Right. So this Q minus Q2. What is this? This is your available energy. Right. This is the available energy. This is unavailable energy. Okay. So this you know. Now let me make the similar sketch for the other one. See, in this case, now this is a fluid at 1000 Kelvin. The moment you start heat transfer from this, the moment it starts giving out heat, its temperature is going to drop, because this is a body of finite heat capacity. Finite. So temperature is going to drop. So I am just removing this now, and okay. When the temperature drops, it will keep on dropping. And what is the maximum value to which it can drop? It will be surrounding temperature, right? That means, let's say 200 Kelvin is the sink temperature, it can drop up to that. It can drop up to that. Okay. So if we want to, now let's say, so it's moving from, the temperature drop is from 1000 to 200, and that is the total amount of heat. Okay. It need not be 200. You can take some other value also. Let's, for simplicity, we'll take some other value, right? So let's say 1000 to 600. Right, 1000 to 600. So what will be the amount of heat that will be flowing out if the temperature is dropping from 1000 to 600? Let's say Q, and that Q will be mCp 1000 minus 600, right? Delta T, let's say mCp delta T. M is mass of this fluid, Cp is the fluid specific heat of the fluid, and delta T is the temperature drop. This will be Q. Okay. Now this Q, of this Q, how much is the available energy? That's what we are interested in. What is the maximum amount of, theoretical maximum amount of work that can be obtained from this? So what we do now, again, let's say we are giving this heat to this Carnot engine. Let's say we are transferring this heat to Carnot engine. Okay. Now, I'm going to correct myself in saying that this may not be considered as Carnot engine, but I'll come to that later. Let's say we follow exactly the same steps. So we are giving the heat to Carnot engine. Okay. We might have to employ many engines. I'll make that point clear as we go ahead. So we are giving heat this. Now how this heat will be given? It has to be given reversibly. Okay. Please note, it has to be given reversibly. That means what? That means the temperature of this and the temperature of the working fluid in the Carnot engine, that they should be same, or they should be infinitesimal temperature difference. Essentially we are saying it's same. Okay. But this temperature is dropping. Okay. So initial it is 1000. When some amount of heat dQ is coming here, this also should be 1000, and heat is received. Then this temperature drops. Next small amount dQ will be transferred at, let's say it is 999.99. This temperature also should be 999.99. So this temperature is dropping. So should this temperature, right? So see, you have to imagine this. So every time the temperature difference between these two engines, these two bodies, that is Carnot engine and this, should be infinitesimally small. Should be infinitesimally small. Okay. Now one can imagine this practically. Let's say, this is a counter flow heat exchanger. Okay. So let's say we are considering 1000 to 600. let's say another fluid entry, and this is, we can say, the fluid in the Carnot engine, imaginary fluid. Okay. Now every time, so heat is transferred from this fluid to this fluid, and let's say this fluid is entering at 600. Okay, this fluid is entering at 600. That means the temperature difference between them is infinitesimal, and this fluid will be heated from 600 to 1000. Right? This fluid which is giving the heat here is dropping from 1000 to 600. Okay, so this is 1000. So what is happening? Every time the heat transfer that is taking place will be infinitesimal. Now if you want, this is a fluid which is used in Carnot engine. Okay, its entropy is going to increase, its temperature is also going to increase. So how will you show that here? On this diagram you can show, let's say this is somewhere 600. Okay, so we can show this as, please note, this is here, this is 1000. So you are moving from 600 to 1000. Okay, 600 to 1000, and this area will be the it will be total heat supplied, total heat Q, that is given by this area. Okay, I hope this is clear. Now we are this 600 to 1000. This is the line. Okay, and then we can do exactly as we did in the previous case. We can say, so this is our heat addition. Then there will be reversible expansion, right? And then there is, heat has to be rejected. All the heat cannot be converted into work in a cycle. So some heat has to be rejected. So this is, okay. So this is your cycle when your body is of finite heat capacity. Now you might ask, this is certainly not a Carnot cycle, because in Carnot cycle you cannot have heat addition has to be at constant temperature. But I would like you to imagine it this way. If I split this, if I draw lines like this, now just consider each of this, each rectangle, right? Because the lines are so close to each other, this can be considered at constant temperature. Okay, so heat addition at each Carnot cycle. So basically, I have split the entire cycle into infinite number of Carnot cycles. And now this is a Carnot cycle. I am sure you will agree with me that this, anybody, this is a Carnot cycle. This is another Carnot cycle. So here you can see this is a Carnot cycle, this constant temperature, because lines are so close to each other, the height difference is negligible. So they are of the same height, that means the temperature is constant. So this is what entire cycle can be converted into infinite Carnot cycles. Okay, so it's not one Carnot cycle, there are infinite Carnot cycles. So when you have finite heat capacity and of a body which has got finite heat capacity and it is giving out heat, and then you want to find out how much of that heat can be converted into work, then all that you have to do is consider not one Carnot cycle but infinite number of Carnot cycles, many Carnot cycles. Okay, but otherwise it's same. See here, this entire thing, if you consider this is your heat supplied, this is heat rejected, this is what? This is unavailable energy, right? This is available energy, and this total is heat supply. This total is heat supply. Total heat supply is MCP delta T. MCP delta T. What is this? Okay, just see this. This is the change in entropy. Okay, what is the change in entropy? Delta S. This fluid, imaginary fluid, is heated from 600 to 1000. This fluid is dropping its temperature from 1000 to 600, but the fluid in Carnot engine will be heated from 600 to 1000. Okay, so entropy change will be MCP ln T2 by T1. T2 is, in this case, we will consider T2 is 1000, so 1000 upon 600. Okay. Also remember that entropy change of this fluid and entropy change of the fluid in the Carnot engine will be same. Why? Because there is reversible heat transfer, right? There is reversible heat transfer, so entropy change will be same. So if you find out entropy change of this fluid, Just change the sign because entropy is decreasing here and whereas entropy of the Carnot engine is increasing. So if you find out entropy change of this fluid, the final temperature is 600. That means it will be 600 upon 1000. But entropy change of the Carnot engine fluid, it will be 1000 upon 600. Just think about it. Okay? And so all that you have to do is consider this fluid. If temperature is dropping, then delta S you have to consider positive because final temperature of Carnot engine is higher. So you find out 1000 by 600. This is delta S. Okay? And what is available energy? See here. This is delta S. This is delta S. This is T naught because 200 is T naught. Okay? T naught into delta S is this. Right? So this is T naught into delta S. Okay? So Q is the heat supplied. The total heat supplied is mCp delta T. So Q minus T naught into delta S. Q minus T naught into delta S is this area. This is the available energy. This is the available energy. This is the maximum work that can be obtained from this heat. Okay. Thank you.